should be okay. No? Okay. Yes? Okay. This talk will be about the realization of topological matter in quantum gases. So I have written here the outline. So there will be 3 parts in the talk. So the first part will be basically about models that are involved in the understanding of maybe the most widespread topological states of matter, which is the systems that exhibit a quantum Hall effect. So I will focus on the structure at the level of single particles that give rise to the integer quantum Hall effect. And more specifically, I will rather focus on Landau levels and speak a little bit about lattice models because they are relevant for cold atoms, but I will not have time to explain this in full details. Then I will discuss the status of experiments on the realization of topological bounds. So of course, the atoms are neutral, so it's not, we cannot have basically a Lorentz force by applying a magnetic field. So we need to apply, to use analogies. And there have been different techniques that have been developed, rotating gases, time-modulated lattices, and I will finish briefly with the concept of synthetic dimensions. So in those systems, basically, the experiments were focused on either non-interacting or weakly interacting systems. And I will switch at the end towards the regime of stronger interactions, where we expect systems analog to those exhibiting a fractional quantum Hall effect. So there, the experiments are much less advanced. And I will focus on the bosonic Laughlin state and explain that it has been realized somehow in a microscopic instance in experiments. And I will explain then how we can imagine extending those systems towards the thermodynamic limit and what we can do with the systems that we would realize, so typically probing the topological order or anionic excitations. Okay, I hope I will manage to cover all that. So let's start with basically the basics of the integer quantum Hall effect. Maybe before starting the first part, I would like to remind what is the integer quantum Hall effect that occurs in 2D electron gases. So I sketch here a planar configuration where there would be electrons that we subject to a perpendicular magnetic field. And then in a 4-terminal geometry, we can measure the existence of a current along the y direction that occurs together with a Hall voltage u along x. And so there is a proportionality between the current along y and the voltage along x that involves the Hall conductance sigma xy. And it was observed in 1980 that at low temperature for 2D electron gases and high magnetic fields, sigma xy is quantized. So it's given by an integer times the quantum of conductance E squared over h. Okay. And very well, when this was observed, it was not directly understood, but very soon. It has been understood in terms of the band structure of the system. And there were links made with a certain kind of ordering of quantum states that exhibit topological properties. So I will not cover the different kinds of topological bonds that we can imagine. I will focus on the simplest configuration, which are the so-called Landau levels. So this is the first section on Landau levels. So which is the model with a minimal ingredient. So we need particles with a charge subjected to a magnetic field, and there is no underlying lattice or additional potential. So it's really an ideal model. And the single particle Hamiltonian is simply given by momentum minus the charge times the vector potential squared over twice the mass. And so I will briefly remind you what is the level structure. Actually, the way to express the levels depends on the symmetries of the problem, and in particular on the choice of the gauge in order to express the vector potential. So in this talk, I will mostly use the symmetric gauge. Which means that the vector potential will be written as 1/2 of B cross R, which is a vector potential along the azimuthal direction E phi, or in Cartesian coordinates. I mean, depending on the situation, I will need the expression in the different coordinates, I think. So like this. So if we want to get quickly the quantum levels, maybe the simplest is to expand this square. And I will first gather the two squares, so p squared and a squared, in the following way: p squared over 2m plus, I mean, this a squared involves basically r, sorry, I forgot r here, involves the square of r. So it can be expressed as an isotropic harmonic trap that can be written as follows: 1/8 of m omega c squared r squared, where omega c is the cyclotron frequency that we know from classical physics. So this is, you see, simply an isotropic harmonic potential. Then the cross product can be expressed as 1/2 of the cyclotron frequency times Lz, so the projection of the angular momentum along Z. And well, from this, it's very easy to write the level structure. So let's start by forgetting the right term. So the harmonic potential, its spectrum is simply given by h bar omega c over 2, because the trapping frequency is omega c over 2 for this potential, times n0 plus 1. And those levels are degenerate, and they can be indexed by the projection of the angular momentum. So Lz is m h bar, and m ranges between minus n0 and n0, but only values of the same parity. So minus n0 plus 2, up to n0. Okay. So if I plot the level structure, energy versus m, so I have on the abscissa integer values, start with 0, 1, minus 1, and so on. So the ground state n0 equals 0 is not degenerate. Then the first excited state is twofold degenerate at m equals minus 1 and 1, and so on. Okay, and it continues. So now, if we want to include the term that I discarded, minus omega c over 2 Lz, I mean, it's proportional to m, so we just need somehow to shift the levels that I have already drawn. And the shift is precisely such that, well, it depends on the value of m, and it's precisely such that all the terms on this diagonal are shifted to the same energy. So I draw the shift, so no shift for m equals 0. For minus 1, I shift up. For minus 2, I shift up by twice the amount. And eventually, I get the full spectrum, which consists in degenerate bounds. So the ground bound starts at m equals 0. And then I have higher bounds. The first excited bound starts at minus 1. And so on, with the spacing h bar omega c. So each of these degenerate families is called the Landau level. And in the following of the talk, I will actually focus on the lowest Landau level, LLL. So for the explanations in the following, so let me try to understand how it works. Okay. I keep that. So I will need to know a little bit what are the eigenstates of the lowest Landau level. So if I focus on one state, I will call this state psi m, and I will give here maybe, well, sorry, I need to lower it down fully. I need to give the main characteristics of those states. So psi m, its wave function is proportional to r to the m, ei m phi, so phi is the azimuthal angle, times a Gaussian factor, e minus r squared over 4l squared, where L is the so-called magnetic length, square root of h bar over qb. And it's important to know how the density is organized in those states. So if I start with the state m equals 0, there is nothing here. So it's simply a Gaussian that I plot here, and the extent is L. So this is for m equals 0. If now I consider a higher value of m, I don't call it excited state because it's degenerate. So m larger than 0, I will have the probability distribution concentrated on a ring that has a certain width. So the width is still of order L, but what will be important in the following is the radius, Rm, that scales as square root over 2m times L. So this radius is not really random. Jokes here, okay. This radius is not really random. We can wonder what is the magnetic flux enclosed by this orbit. It will be important in the following. So I call this phi m. So it's the magnetic flux, which is simply b times the area, so pi rm squared. And we get b times 2 pi m, L squared is h bar over qb. So we get m times h over q, which is the so-called quantum of conductance, quantum of flux quantum, sorry, flux quantum, and that I will call phi 0. Okay. So let me check, but I think that's all I needed to say about those states. So far I have considered an infinite plane without boundaries. And maybe to be a bit more concrete, we can also wonder what happens if we consider a finite system. So I will consider a system in the presence of a box potential. I will use a circular box in order to maintain the rotational symmetry with a radius r, capital R. And this box potential will actually lift the degeneracy between the states of the Landau level. But of course, what we expect is that for states that are located within the area of the box, so states with Rm smaller than R do not change. And if we consider a higher value of m, so maybe I have to say that I want to define m max such that our m max is equal to R. So maybe before considering the other states, I can start plotting the spectrum E versus M. So I start at 0, and for all the states up to M max, I still keep almost a degenerate structure. And then if I consider a state with M higher than M max, I mean the wave function that we obtained earlier is located outside the box, so it's not possible. So actually it will become concentrated close to the edge, and this will come with an increase of the kinetic energy because the system is localized, and so the energy will rise. And this part is what we call the bulk states, while these ones are the edge modes. Edge states. So those states are dispersive. So maybe I have drawn already the wave function for the bulk state somehow. So if I plot maybe the density of the edge modes, so they will be located very close to the edge here. Something that is important also is that there is a non-zero velocity, so v phi, so the azimuthal velocity is larger than 0. So actually v phi is more or less given by r omega c times m minus m max. So it increases when we increase the value of n. While for bulk states, I mean, they are basically at rest. Okay. I think that's, I wanted to say one more thing. So now the last thing I want to introduce is how do a generic state of the Landau level look like? A generic state. I will focus on the generic state in the bulk, meaning that I will consider a wave function that expands over the states with m between 0 and m max. So generic wave function will be given by the sum over m ranging between 0 and m max of an amplitude Cm times psi m. I remind that, I mean, it's written here, psi m is given by r to the m ei m phi. And we need to see that r ei phi is nothing but x plus iy, which is the complex coordinate z. And so it's convenient to express this wave function in terms of this complex coordinate z. And so we get Cm z to the m times a global Gaussian factor that is the same for all psi m's, so e minus r squared over 4l squared. Actually, in the following, I will no longer write this Gaussian factor. So I put a cross, so I will no longer consider it because it's always the same. So you see that we are left with a polynomial of the variable z, polynomial of order m max. And that's a convenient writing because, well, for instance, we know that we can factorize the polynomial in terms of its roots. So, I mean, it's natural to write it. Maybe I should put proportional as a product over the roots, k, between 1 and m max, of z minus zk. And so this shows that a generic wave function of the Landau level that occupies significantly all the states between 0 and m max will have a series of zeros, the number m max, and so the wave function will be pierced by densities, by points of zero density. So if I plot now a generic wave function in the xy plane in my box, so I have the box here. So I will have non-zero density everywhere. But on top of that, I will change color so that it's clear. I will have a series of m max holes that I draw as crosses. And we can check that actually if we follow the complex phase of the wave function when we encircle one of these roots, it increases by 2 pi. So it means that this is a quantized vortex. And so to summarize, I mean, a generic state of Landau level is determined by the position of this series of vortices. Okay. Can lift up this. So final word on Landau levels. So how to understand the quantization of the whole conductance. So it's the part 1, 2, quantization of sigma xy. So I will keep again a geometry with a rotational symmetry. And actually, I will slightly modify it. I will consider an annulus geometry with an inner radius and an outer radius. So basically, yes, this is also called Corbino geometry. I will explain why I want this. So the idea, since I have this rotational symmetry, I will not write a relationship Iy equals sigma xy ux. It's not adapted. I would prefer to apply a voltage, let's say, in the azimuthal direction and look for a radial current. And in order to have an azimuthal voltage, U phi, I will need to insert a solenoid here. It's a solenoid that allows to insert a magnetic flux phi. And then we know from the laws of inductance that the U phi is simply given by minus phi dot. So it's a way to somehow create an azimuthal voltage. So then, in order to understand why we have a radial current, well, we have maybe to understand what happens when we change slowly the magnetic flux. So let's start with phi equals 0 and assume that we start in the state psi m. And we increase, so it should be adiabatic, we increase phi up to 1 unit of flux quantum phi 0. So then it's easy to understand what happens because I remind that psi m, it encloses a flux which I called phi m, like this, which was m phi 0. So if I increase the flux inside this inner radius by 1 unit, I add phi 0, I have to end up in a state that will have a flux phi m plus 1 phi 0. And so necessarily, I have to transfer psi m to psi m plus 1. Okay? And so it means that each time I insert 1 unit of flux quantum, I have all states of the Landau levels are pumped from m to m plus 1. This is a so-called Laughlin pump. And then what is the current in the radial direction? I mean, it's simply given by one charge Q. Each time the flux increases by phi naught, so it's phi dot over phi naught. And phi dot, I said that it's minus u phi. So I have minus q u phi and phi 0. I remind that it's h over q, so I get q squared over h. So I find again the quantization of the whole conductance. Okay, I think that's it for the Landau levels. Briefly, as I said, I will discuss very briefly, because time goes on, the case of the extension to lattice systems. I mean, it's very rich, and it would take a bit of time to explain it in full details. But I will simply explain how it works in order to introduce a few elements that I need in the following. So let's start with, let's say we start from Landau levels. And our goal is to express a quantum Hall effect in a lattice system. So simply, the simplest way to think of it is to simply discretize space along a square grid, a square lattice. And so I will have only discrete positions. And the underlying Landau level has a uniform magnetic field. So when we do that, so if we want to write a tight bending model, so this is the so-called Harper-Hofstadter model. Well, we need simply to say how the particles can be transferred from one site to a neighboring site. So if we do that in the absence of magnetic field, we start from particles evolving on a plane, and we discretize space. And then the hopping matrix element can be all chosen real. That's the standard tunnel matrix element, if you want, or hopping matrix element. And so now if we have a magnetic field, the situation changes because the motion is associated with a geometrical phase, which is so-called Aharonov-Bohm phase. And so the hopping between a position Ri to a position Rf occurs with a tunnel matrix element that I call J Ei phi, where phi is given by the Aharonov-Bohm phase that the charge acquires when going from Ri to Rf. And it is given by the line integral of the vector potential Okay, so this is the Aharonov-Bohm phase, and the phase we get for the connection between two sides changes name. It becomes a Peyer's phase. Okay, so as I said at the beginning, we can choose different gauges. So I mean the pattern of phases depend on the choice of gauge. But what really defines the model we consider is something that is gauge invariant. I redraw the lattice. What is gauge invariant is the accumulated phase over a closed contour. So here an elementary unit cell. So phi cell. And we can easily see that it is given by 2 pi times the flux phi. I will say what it is divided by the flux quantum. So this is the flux quantum. And this is the flux of the magnetic field I impose over the unit cell. So if I call A the lattice spacing, it's BA squared. And so this is phi cell. And so the model is actually determined by the value of phi cell. So actually there are different Harper-Stater models depending on the choice of phi cell. So in general, it's a complicated bond structure because the fact that we have position-dependent phases means that we have lost translational invariance. So in the general case, there is no longer Brillouin zone and so on. But well, there is an exception that we always consider, the case of phi cell, which is an integer, so 2 pi times p, not an integer, sorry, a rational value, p over q, which is such that if you take q sides, so I will take the example, let's say of p over q equal 1/3. Then if I take a unit cell like this that contains 3 sides, this is called magnetic unit cell, then it encloses a total flux which is phi naught. And then the system becomes translationally invariant with respect to translation of this magnetic unit cell. So we recover a bond structure, except that since this magnetic unit cell contains several sites, there will be several bonds. Instead of the single bond of the square lattice with real matrix element, we get several bonds. So if I plot E versus, let's say, QX, so I get, let's say, on this example, 3 bonds that I sketch like this. And then the lowest bond is somehow equivalent to the lowest Landau level. It becomes actually very close in terms of all properties, close to the lowest Landau level when P over Q tends to a very small value, so 1 over Q with large values of Q, because then the lattice discretization is irrelevant. But in the most generic case, I mean, what we lose is that the lowest bond is no longer degenerate, but still it has the same topological properties. It has quantized sigma xy, which is given still by q squared over h times an integer here that changes name. It's the so-called Chern number, which characterizes the topological structure of the bond that we consider. And so in practice, the lowest bound, if we take P over Q is 1 over Q, it has C equals 1, then it's equivalent to the lowest Landau level somehow. Okay. I will not really elaborate more. Maybe something that I want to say before I forget, that what I've done is a sort of construction of the Harper-Stater model starting from Landau levels and discretizing by hand. But we can also imagine more complex lattices, like the famous Haldane model, which cannot be understood in terms of starting with a uniform magnetic field and discretizing. But somehow, as soon as you consider a lattice system with complex phases, such that there is a breaking of time reversal symmetry, you can have non-zero Chern numbers and the same physics. Okay. So that's it for the first part. So now I will move to the second part about experiments.
May I ask a quick question?
Yes.
When you got the quantized conductance, probably basically the degeneracy factor, which gives you then the plateaus as an integer number because you have integer quantization.
So here I didn't put an integer, yes, because I was considering the lowest Landau level only.
But the series of integer quantum Hall conductances comes because
Yes, I would need to include higher Landau levels to have an integer here, yes.
But if one would do this experiment in an idealized geometry or with cold atoms, you would not find a quantization, because the quantization only happens when you have a filled Landau level.
Yes, this is, yes.
Whereas if you would continuously change the number of Landau levels, you would get actually a continuous change of the conductance. The question is, I do feel in discussions with my many condensed matter physics,
I assume in
there's always a question of, Anderson localization, disorder, and
I assumed here implicitly that each state was filled with one atom. Because I said that each time the flux increases by phi naught, I have one particle that is transferred. So I was implicitly assuming, I should have said it maybe, but there was one particle per state. Yes.
One perhaps should also add that the connection between sort of the Chern number and the sigma x y, of course, we assume sort of your Fermi energy or your chemical potential is in a gap.
Yes. Yes. Yes.
That's a crucial.
Yes. Okay. So second part. Maybe I can switch board. So we'll start with the first technique that gives rise to quantum Hall physics, which is, so it's the part 2.1, rotating gases. And actually, I made on purpose the introduction on Landau levels in the symmetric gauge and explaining slowly that we can decompose the Hamiltonian in terms of an isotropic harmonic trap and an angular momentum term. And so it will be fast to understand the connection with rotating gases. So here we consider so neutral atoms, so atoms in an isotropic harmonic trap of frequency omega. Then the Hamiltonian is p squared over 2m plus 1/2 of m omega squared r squared. And this looks like the first part that I've written here. In order to get the last term, you have to remember that if we consider a physical system in a non-inertial rotating frame, then in the rotated coordinates, in the rotating frame, the Hamiltonian has to be expressed as the Hamiltonian in the lab frame minus the rotational frequency omega rot times Lz. And so we have all the terms needed to mimic the Landau levels. So we have Landau levels for omega equals omega c over 2. So basically there is a link between the trapping frequency and the cyclotron frequency. But more importantly, when we fine-tune the rotation frequency, exactly equal to the trapping frequency. And then, we have exactly the same structure. So this was basically the starting point of many experiments that were done with BECs. Bose-Einstein condensate. So in Paris, also in the group of Wolfgang, and so on, and the group of Eric Cornell as well, and well, many experiments. And there, the situation is that those experiments were performed with many atoms. So N hat was much larger than the number of orbitals of the lowest Landau level, which is somehow, if I keep the same notation, m max plus 1 in my earlier definition. So actually, I have to say that, I simplify a little bit the picture, because in the experiments that were performed, the atomic gases were not restricted to the lowest Landau level. They were actually occupying many excited bands as well. But the physics is somehow a bit magically the same than if the atoms were restricted in the lowest Landau level in that case. So I will do as if they were restricted to the lowest Landau level. Okay, yes?
Why do you need the Poincaré condensate to do this kind of experiment?
Well, I'm explaining what has been done. I will then explain what happens when we go to the strongly interacting regime, where we reduce the number of particles, then the physics changes. But most of the experiments, because they are simpler to do, were performed in this regime. So in this situation, where you have many atoms per orbital, then the system remains described as a Bose-Einstein condensate, meaning by a classical field.
Sylvain, I think the answer is, in those rotating experiments, we were able to see the vortices.
Yes.
But if you have vortices for a single atom, you cannot see them. But if you have a macroscopic population, a macroscopic wave function, you can
Yes.
see the vortices. So in other words, the Bose-Einstein condensate allowed us to see
Yes.
vortices
Yes.
in a macroscopic way, which would not be. I think that's probably the reason why the Bose-Einstein condensate was needed to do the vortex experiments.
Yes, that's true. Yes. Mhm. Okay, so we can describe the system by a classical field, psi, which is somehow the macroscopic wave function in which all the atoms, that's all the atoms occupy. And then this state, I will write it simply as a state of the Landau levels, of the lowest Landau level, for simplicity. And so, as I said, it is determined by the position of vortices. So the question is, how do the vortices organized in those experiments? So I said before that the lowest Landau level is degenerate, so all positions of vortices are a priori equivalent if we only consider single particle physics. So the position of vortices was actually fixed by interaction effects. So they play a very important role in the understanding of the organization of vortices. And those interactions in cold gases between two atoms at positions R1, R2. So they interact mostly via van der Waals interactions that are of short range. And we can basically approximate them to a very good approximation, as Sylvain explained in his lecture, by a contact potential, so a coupling constant G times a Dirac function, R1 minus R2. And we take G positive, so repulsive interactions. So then the interaction energy, so there is no kinetic energy somehow, because all the states are equivalent in energy at the single particle level. So we are left with interaction energy, which is simply G times n minus 1 over 2 times the integral over space of psi 4. Okay. So the system wants basically to minimize energy to have a profile, density profile that is as uniform as possible. So in the absence of magnetic field, for example, it's clear that we minimize the interaction energy by having all atoms in a given momentum state P equals 0. So it gives rise to a uniform density profile, except that there are edge effects, but uniform density profile. But we have seen that this is not possible in the Landau levels, because if we want to spread the wave function over the full box, then we need to have vortices in the wave function. So the question is rather, how do vortices organize in order to minimize this interaction energy? And we get Abrikosov, a regular array as first computed by Abrikosov for the vortices organized like this. So Abrikosov, triangular lattice. And so this was observed and studied in many beautiful experiments with BEC. And as Wolfgang says, if we take a snapshot of the density profile, we can see holes, basically, because there are many particles per vortex. So we have a well-defined, smooth density profile. We can forget about the discretization from the particles if we are in this regime of many atoms. Maybe time goes on. So I would like maybe to, I wanted to say a few words on recent experiments on rotating gases. Maybe I will be faster than what I planned because time goes on. So rotation has been studied in detail in the early days of Bose-Einstein condensation. And then somehow people reoriented research. There were fewer experiments done on rotating gases because there were some difficulties to reach the interesting regime of strong interactions. Because basically in rotations there are some intrinsic technical difficulties that I can list. So the first one is that basically as soon as you have a little defect in the potential that contains the atoms, a defect that is static in the lab frame, it turns into a rotating defect in the rotating frame, and so it leads to time-modulated potential and then heating of the atomic gas. So that's maybe one of the limitations, but it's purely technical, so in principle it can be solved. And another thing is that to set gases in rotation, we need to apply a deformation that rotates, so that is static in the rotating frame. But this deformation somehow breaks the degeneracy between all the states of the Landau level. So it's another complication. This deformation may have a non-perturbative effect. So these are technical difficulties, but that were somehow overcome recently in beautiful experiments in the group of Martin Zuerlein with so new experiments where he could take advantage of modern tools in cold atoms, namely the ability to look at the gas in situ with high imaging resolution, and also the ability to make box potentials. And so in these experiments, it was really possible to study rotating gases in a box potential with rotational symmetry. And the experiment was the following. So he was starting, his group was starting with a round Bose-Einstein condensate. And then a quadrupolar deformation was applied. So V of R, which is minus QXY. Quadrupolar deformation was applied, so a rotating one, but I write it in the rotating frame here. And we know that charged particles subjected to a magnetic field follows equipotential lines. So if I plot here the values of the potential like this, so the equipotential lines are like this. And what it leads is in practice, a compression along the y direction in my graph and an elongation in the x direction. So eventually, they could measure a very elongated trap. And what is beautiful is that this corresponds to a LLL wave function almost purely in a single LLL state, but that we have to understand in a different gauge. So far I introduced a symmetric gauge, but if instead I would have introduced the Landau gauge, meaning that the vector potential would be expressed as minus by Ex. So if I had chosen this gauge, then there will be translational invariance along X. And then the wave function, instead of being a psi m, the natural basis would be a psi kx, momentum along X. And it would be a plane wave along X, and along Y it's more complicated. So in practice it's a Gaussian along Y, and the center of the Gaussian depends on kx, but it is not very important for what I want to say. So it's phi kx of Y. And so here, what happens, since it's a symmetric configuration, they realized actually, they realize psi kx equals 0. So this is just to say that with modern tools, with access to microscopic details of the density profile, we can really study Bose-Einstein condensates at the level of single LLL wave functions. And a second experiment they have made is to switch off this deformation and let interactions act. And what they could observe, so interactions, they could observe that there were collisions between atoms in kx equals 0 towards, let's say, plus k plus minus k. I don't specify the value of k. So it means that now the wave function acquires different momenta, so it will break translational invariance. And in practice, the wave function wiggles. So like sketch is like this. So maybe I exaggerate a bit the wiggling, but okay. And actually, there are quantized vortices that govern this wiggling. They could observe the appearance of those vortices. And so I think this shows that we can really track the effect of interactions and the interplay with the ordering of vortices, maybe towards Abrikosov vortex lattices, really at the microscopic level. So I think those experiments are very interesting. They show that rotating gases are still a very active field of research. Okay, now I will switch to lattice systems. So lattice system, I remind you that what we need is to engineer Pierre's phases, so complex value matrix elements. So yeah, Pierre's phase engineering. And the protocol was given by a seminal paper by Jaksch and Zoller. And I start by sketching a simplified protocol, which is the one that corresponds more closely to what has been implemented in the experiment. So what they propose is to use an optical lattice and to tilt it, to apply a potential tilt. So the lattice is like this, so that the successive states, so this would be X, and let's say the lattice is flat along Y, so that the different wells along X are shifted by an energy h bar delta, large enough to prevent spontaneous tunneling. And then we shine on the atoms pair of lasers, so for example, counterpropagating. So here it's along Y. And the two lasers should have different frequencies, omega and omega plus delta, so that they can induce Bragg transitions, basically connecting neighboring whales in this way. So this corresponds to a Bragg-assisted tunneling of atoms. And in doing so, maybe I should sketch. So this would be, let's say, E1. This would the electric fields are E1, E2, and so the effective tunneling will be proportional to the amplitude of E1 times the complex conjugate of the amplitude of E2, because we absorb a photon from this laser and emit in stimulated emission in the second mode. And so it will be proportional to EI delta K Y. So delta K is the difference between the light momenta of the two lasers. So what we see is that the motion along X involves a hopping matrix element that have a complex phase that depends on the value of Y. And so this crosstalk between X and Y is equivalent to the application of a magnetic field. And with that, it was possible to simulate the Harper-Hofstadter model, and with similar techniques, the Haldane model. So it was done in many groups, maybe first in Munich, in the group of Wolfgang, in the group of Tillman-Esslinger on the Haldane model, but it was then studied by many groups. So how do the quantum Hall physics manifest? So I would like to explain manifestation of the quantum Hall physics. One experiment that was done in the Munich group where they implemented the Harper-Hofstadter model, and they loaded a large number of bosons in it. So I sketch roughly the system like this. And then they applied a force along the X direction, and then they were measuring the drift in the transverse direction. So the evolution of the mean value of Y, so I mean in the center of mass position. And so they were measuring the whole drift. So Y was evolving proportionality to the force Fx to time. And then, I don't want to make mistakes, so I look at my notes. 4a squared over h bar. A is the lattice spacing. And then there was an additional factor, which is the chair number of the occupied band. So they could somehow measure the proportionality factor between the drift and the force, and they showed that it was consistent with a unit chair number, even if the lattice parameters were changed by small amounts. So this was consistent with unit quantization of the chair number. So actually, to be more precise, because this will be important to explain the limitations of the method, the evolution was rather like this. So it was starting linearly, and then it was kind of saturating. So the initial slope was consistent with c equals 1, but we would expect that it continues. And the fact that it was saturating is because there were some inelastic effects that I will explain briefly in the following that lead actually to the incoherent population of higher bands. So I said that the Hofstadter model has several bands. And so they started in the ground band, and progressively they were populating many bands. And this leads to a modification and eventually to a saturation of the response. Yes? Okay. So this shows that, well, we can make beautiful experiments with these time-modulated lattices. So lattices subjected to Bragg beams. But at the same time, that there are some limitations in the method. So the coherence time is limited. And this is due to the fact that the Bragg beams, they generate a time-dependent potential. So V Bragg is proportional to cosine delta K R minus delta T. So the delta is there precisely to bring the energy required to hop from one side to another. So it's time dependent. And so the Rapper-Stator model is somehow an effective static model that we get if we make the right rotating wave approximation and discard oscillating terms. But these oscillating terms still exist, and they can give rise to problems. So basically, there are different ways the atoms can absorb the energy of the modulation, so this h bar delta, and end up in the wrong state. Instead of hopping, they can end up in higher bands. In the tilted case, in plus higher bands can be connected with states that leak to the left, so we can lose the atoms. We can also imagine that there can be collisions between atoms that are affected by the modulation frequency. So you can imagine processes where two atoms enter in collision, and via the collision, they absorb one or several quanta of modulation energy. And this gives rise to heating and to incoherent effects. So how to solve issues of time modulation? Maybe I can explain how so far people have worked. I mean, basically, you can minimize those effects by choosing well the value of delta, of course. So you need delta to be large enough so that these wrong oscillating terms can be averaged to 0, but you should also avoid resonances towards higher bands, so there are some sweet spots, but still the heating is non-negligible. So, well, if we want to solve, maybe we have to go back to the original proposal of Jaksch and Zoller, because I said that I simplified it. And I would like to sketch rather the first figure of their proposal. In their proposal, they were considering a spin-full system. So a spin 1/2 system. So there were two optical lattices that were actually in an anti-magic configuration. So where you have a maxima for one spin, you have a minimum. So we try to draw that the correct way, like this. So the wells are like this. So this would be for spin up and spin down, let's say. And then the hopping, assisted by lasers, should be done together with a spin flip. So then it corresponds to Raman transition. And then the difference in energy, delta, it becomes dominantly given by the difference in energy required to flip the spin. So it depends on the spin state, the effective spin state you use, but it can be a hyperfine spin. It can be also a difference between electronic levels. So it becomes hyperfine splitting or even electronic splitting. So in that way, you can make the splitting or the value of delta extremely large, and so large that it becomes irrelevant to imagine an effect of this oscillating term that we want to discard. So I think that's really something that several groups try to pursue in this direction, and probably it will solve many issues of time-modulated lattices. So I see that time passes.
Excuse
Yes?
You didn't mention disorder in this academic system, or
Yes.
should play a role, or some kind of disorder? Because in condensed matter, in quantum monetary condensed matter, disorder is very important, right, to explain the quantization.
Yes, so here that's a little bit different. Well, first, in cold atoms, disorder can be made quite small. So I would say that there is almost no disorder. And then in condensed matter physics, it's important to understand the effect of disorder is crucial when we set the chemical potential between two bonds to say that basically when a bond is not filled, it does not contribute to whole quantization because of localization effect. So here, actually, in this experiment, for example, what we measure, I mean, the filling is irrelevant because this experiment was measuring a drift of the center of mass, and I did not specify that actually it was made with a Bose-Einstein condensate. Well, actually not really, but with bosonic particles. And this result does not depend on the filling, but rather on the fact that we should occupy incoherently the ground bound with basically occupying all the momentum states of the ground bound in equal terms. So I don't think we need an argument of disorder to understand the quantization. Okay, maybe briefly, but I will also be more brief than what I expected. The last method are synthetic dimensions. Synthetic dimensions. So it's a powerful tool, I think, to engineer topological bonds. And the idea is to replace the one direction, y, by an internal degree of freedom. So there are different possibilities, but what I will use is the spin of the atom, so a spin j, and the dimension will correspond to the values mj of the spin projection along a given axis. So it will take half integer or integer values between minus j and j. And so the system becomes an xmj plane where we have a series of wires like this, and that correspond to the discrete values of mj between plus j and minus j. So then it's very easy in this system to engineer a magnetic field. We just need to make a Raman transition. I already introduced what it is. A Raman transition with two counterpropagating lasers that transfer the atoms from m to m plus 1. So this drives the dynamics along the synthetic dimension. And as I already explained, so this comes together with a complex phase, which is here the difference in the momentum of the two lasers times the position x. So, I mean, it's really equivalent to what I already explained. But that's it. We only need this ingredient, so it's very simple. Only dynamics along x and dynamics along the spin direction. Maybe I will, I will switch to I will not elaborate more on that, and I will switch to the last part. So the last part is towards the regime of the fractional quantum Hall physics. where we need to consider a strongly interacting regime where the filling of each orbital will be of order unity. So the system will no longer be described by a Bose-Einstein condensate or macroscopic wave function. And I will focus on maybe the simplest of those states, which is the bosonic Laughlin state. Because it's probably the first one that will be realized in the experiments. It's probably the one that is the most stable and the most natural to appear given the type of interactions we have in cold gases. So we need to consider bosons, spinless, and I remind you that the interaction is a contact interaction. And so far, when I was considering Bose-Einstein condensates, well, maybe no. Sorry. Okay, so maybe something that we can say is that since the lowest Landau level is degenerate, so I already said that all the energy consists in the interaction energy, and we can wonder whether we can form many body states that minimize this interaction energy. Since we have contact interactions, we just need to make sure that the particles cannot touch each other. So in other words, the relative wave function of two particles cancels at position 0. So let's say for two particles, then the many body wave function that depends on Z1, Z2. We can express it in terms of center of mass wave function, Z1 plus Z2 over 2, times relative wave function, Z1 minus Z2. So since we have bosons, this must be an even function. The relative wave function must be even because we have bosons. And then the interaction energy will be 0 if the relative wave function cancels at 0 relative distance. And so we can exhibit the simplest wave function that satisfies this. So of course there are plenty of solutions, but if we focus on the one that have the smallest extent around r equals 0, so the smallest values of angular momentum, it will be given simply by setting center of mass wave function to 1 and the relative wave function to the polynomial of order 2, so Z1 minus Z2 squared. So this is the so-called Laughlin wave function for two particles, and it's clear that it has 0 interaction energy. And we can obviously generalize to the many body case to write the so-called Laughlin wave function, which is simply a product over all pairs of Zi minus Zj squared. So we can first look a little bit at the properties of this state. First, what is the density profile and the occupation of orbitals? So what is the maximum degree of the polynomial in, let's say, Z1? So Z1 comes in terms of Z1 minus Zj squared. So the number of those squares is n minus 1. And so the maximum number of m that will be occupied is 2, because of the square, times n minus 1. So it means that the density will occupy space up to a radius r max. I remind you that it was square root of 2m times L, so square root of 2m max times L, so which is, well, maybe I can continue. Maybe I will rather be interested in the area. So the area, which is pi r max squared, so it will be given by 2 pi times 2n minus 1 L squared. That I want to write as 2 times 2 pi L squared times, and I will discard the minus 1, assuming that n is large. So what we see is that the area scales as n. So it means that it behaves like a liquid of fixed density. And indeed, the density rho of r, as a function of r, is a plateau. Then there is a little bump, but it's not very important. It looks like this, where the plateau is at a value 1/2 of rho 0. So rho 0 is 1 over 2 pi L squared. It is the density that you would get if you fill each orbital with one atom. So what we get here is half of it, which is one way to say that the Laughlin state occurs at half filling. Okay, so I will explain more properties in the following, but maybe with that I can already explain what is the state of the art in experiment. So very recently, there was an experiment in the group of Marcus Greiner that realized a Laughlin state made of two particles. So really a minimal version of a Laughlin state. So it was in a lattice that was simulating the Harper-Statter model. So it was maybe I don't make the drawing very well. It was a 4x4 lattice. It was bounded by walls made by lasers. So 4x4 lattice. So there are 16 sides. So maybe 16 sides, 9 unit cells, and the flux here was 2 pi around 2 pi over 3, which means that the phi over phi naught was 1/3, sorry, and the total flux phi tot over phi naught was 9 times 1/3, which was 3. And when you compute how many flux quanta you have over the entire system, it gives you the number of orbitals that you have in the ground bound in your finite system. So this we can call it n orb. And this is precisely the number of orbitals you need to construct the Laughlin wave function. Because if we look at this, we take capital N equals 1, so we get 2. So M max is 2. So it means that M can be 0, 1, or 2. So 3 values. So this was the right geometry to produce a Laughlin state. And indeed, by loading adiabatically the lattice in the right, with the right procedure, they could produce the Laughlin state. So maybe the most important manifestation was by basically looking at this behavior. They could measure the density of the system. So of course, it's a minimal system with edge effects. So in order to get basically this plateau value, they were only looking at the central sides here. This is a sort of bulk. And they could measure that rho was, I think, 0.6 with an error bar of 1. Error bar of 1 or 2, I don't remember. I should have checked, sorry. That rho was 0.6 times rho 0. Somehow, so this value first is close to the expected value. We cannot really hope better because it's a really finite system, so there are plenty of edge effects. I want to say that actually measuring this plateau of density, it's not only measurement of the density of the Laughlin state, but it has a direct connection with the Hall conductance, thanks to the so-called Streda formula. So Streda formula, which states that the sigma xy can be expressed as the derivative of the density with respect to magnetic field. And here, in this expression, rho 0, so we expect to have 1/2 of rho 0. So rho 0 scales as 1 over L squared, so it's proportional to the magnetic field. And so we expect, indeed, that the density scales linearly with the magnetic field. And this is actually what they measured. I have to say that they rather measured the slope of the density with respect to magnetic field, to be more precise. Maybe I was a bit too fast with that. And so they claim that via the so-called Streda formula, this was consistent with half-quantized Hall conductance. Okay, so this is the status. Of course, I mean, this is a minimal microscopic system, so we need to increase the system size to really pretend measuring things that are close to the thermodynamic limit. And I want to explain what are the possibilities to increase the system size, increasing n. And this is really the tough part for experiments. So I think there are two classes of possibilities. So either adiabatic preparation, and there are many different proposals, but maybe one that is inspired from these recent experiments is to say, let's start with a series of two-particle Laughlin states, as already realized, and then let's introduce adiabatically tunnel couplings between them. And if we do it in the right way, we can imagine to grow Laughlin states towards larger sizes. Of course, this is very difficult because, we need to be ideally adiabatic to prepare the many-body ground state. So, it's difficult to anticipate what will be the limitation, but it will probably be difficult to reach very large Laughlin state with more than 10 particles, let's say. But maybe the limit will be even earlier. Maybe another way that looks promising, but it has not been so much considered in the literature, is to get inspired from what has been done for the studies of the Fermi-Hubbard model, where the lower temperatures were using the degree of freedom of coupling the system of interest with the reservoir. So if I sketch basically the system I have in mind, that it's a quick sketch of the idea. So there would be in the center, let's say the Harper-Stater model, for example, where we target to create the Laughlin state. And here there will be a reservoir, maybe non-topological. So some parameter will be different so that the system is non-topological, does not have a gap in particular. And then we can imagine that by lowering this energy adiabatically, if we have thermal excitations in the Laughlin wave function, they would delocalize in the reservoir so that in the system of interest, you end up in the very low entropy state. Okay, so this is the idea. The practical implementation, I don't even believe that there is a clear proposal for that, so we have to see what would be in practice the reservoir. But I think maybe to create really systems with a significant size, maybe it's a promising approach. Okay. So now I would like to explain what we could do if we imagine that we have prepared this many-modi ground state, that would be really exciting. So beyond the measurement of sigma xy, so one would be to measure topological order. Topological order, maybe its definition is that if you prepare the Laughlin state on a torus geometry, you expect ground state degeneracy. So this is not a very practical definition for an experiment, but maybe something more suited to experiment is to consider the entanglement entropy. So imagine that you have a Laughlin state. So this sort of liquid drop here, and that you cut the system in two parts. One part A, one part B. And then you consider the reduced system rho A by tracing over B your macroscopic wave function psi. And then, because you have entanglement between the two, rho A will be a mixed state, and you can quantify this degree, the strength of entanglement via the so-called entanglement entropy, which is minus trace of rho A log rho A. So this is the von Neumann entanglement entropy. And we expect that, also, if there was only short-range entanglement, we expect that the entanglement between A and B is concentrated around the cut here. I will not draw this, because I want to introduce the length of the cut, L. And so we expect that since it's concentrated around this cut, that it should scale as L. Then in a topological system, we expect, because of topological order, to have a longer range entanglement, a long-range entanglement, that will modify this scaling with a subleading term, minus gamma, which is so-called topological entropy. That is characteristic of the topological order. So if I want to be brief, because time passes, this is something that we can imagine measuring in the experiments, following experiments that were done first in the group of Marcus Greiner by measuring SA by many-body interference. So actually what we can measure, what I will sketch, is not really the same entropy, it's rather the Rényi entropy, which is minus trace of rho A squared. So it's not the same entropy, but it's maybe related, and maybe it has the same behavior, and it could be used to find the topological entropy. To measure it, the idea is the following. You prepare two copies of the same system, and you make interference between them, meaning that as if you were passing them in a beam splitter. I will explain a little bit more. So for example, you can imagine that you have a barrier between the two. You lower the barriers, which leads to tunneling, and you wait 1/4 of the tunneling period, so that particles are transferred equally on both sides. So when we do that for a pure state, so pure state, psi, then after beam splitting, we know that we have the Hanbury-Brown and Twist effect. So on each side, we will have an even number of particles, even n. And so if we have now a mixed state, rho A, then we will not have an even number of particles, but we will have the mean value of the parity of n that will be equal to minus trace of rho A squared. Sorry, I forgot a log here. Okay. So the purity can be expressed in terms of the parity here of. Sorry, then there is no. I was confused. So the parity of the number of particles will give access to the purity, and hence by taking the log of the Renyi entropy. So the idea would be the following, more precisely. We would start with two copies of the same systems with particles located here. Then we make this beam splitting operation. Then we would have a certain number of particles. And we look only at one of the two systems. And then we count how many particles we have on a certain radius, little r. And the total radius would be capital R. And so we expect that the parity, as a function of little r, should. So if little r is 0, there is no particle, so the parity is 1. If little r is capital R, then we have the whole system, and since it's a pure state, we will get 1 as well. And in between, it will decrease. So ideally, we measure things like this. And if we take the log, then we would have the entanglement entropy that should scale like this as a function of R. And basically, there should be a linear regime here where the intercept with the y-axis should give topological entanglement entropy. So this is maybe one experiment that we could imagine doing to extract the entanglement entropy. I see that I don't have time maybe to elaborate. So can I say a few words on quasi-holes? Very quickly.
What do you mean a few words?
3 minutes.
3 minutes, okay.
I will not write equations, only drawings for quasi-holes. I think it's the 5th. Quasi-holes. So what is maybe the most exciting about these Laughlin states are the quasi-holes excitations that could be realized by sending a focused laser beam, a repulsive potential, on the system that would create here a hole. And then we assume that this laser should be very well localized. And then deficit of particles as a function of the power of the laser is expected to scale like this. So at some point, we create a full hole, well-contrasted hole, and we expect that this deficit should be a fractionalized particle that correspond to this fractionalized quasi-hole excitation of the Laughlin state. So this would be a very nice experiment to make. And furthermore, we can also be interested in the density profile of this quasi-hole excitation. This is something that Jacopo has revealed a few years ago. Since I said that there is a relationship between the radius of the orbits and the angular momentum, somehow the RMS size of the hole here is linked with the angular momentum variation created by this quasi-hole. And this should be h, if we make calculations, we get h bar over 1/4, h bar times 1/4. And if we interpret this in terms of an effective spin associated with the quasi-hole, this leads to the fact that the quasi-hole has a fractionalized spin that is neither fermionic nor bosonic, not half integer or integer. And this is a manifestation of the fractional statistics of these quasi-hole experiments. So we could imagine then measure more directly the quasi-hole statistics in an interferometric experiment where we would rotate one quasi-hole around another. And this should come together with a geometrical phase that we could imagine measuring in an experiment. So I don't have time to explain what are the conditions for it to work. I wanted to explain what would be challenging in this measurement, but okay. Maybe I have to stop here. Thank you.
Thank you.